standing waves is the phenomenon that you've just seen. It's important because it occurs all around us, from musical instruments to appliances, and even down to quantum level. Before exploring its applications, we need to first understand the mathematical foundation of standing waves, a topic covered in FAST 1246.
Now, what are standing waves? Standing waves are nothing else but a special kind of waves, a wave in which its points seem to be spatially invariant, in other words, seems to be standing. But how do they form? As we can see in this animation, the standing waves are nothing else but the results of two waves interfering with each other, but not any kind of waves. They need to share amplitude but have opposite directions. To illustrate this, we'll use the example of a string attached in one of its ends to a wall and with the other end attached to a driving force. As soon as we start shaking the string, transversal waves will start traveling throughout the string, only to face the wall and bounce back, traveling with the opposite direction and starting to interfere with incoming waves. This will generate an interference pattern, standing waves. In standing waves, we can appreciate two characteristic points: the node, points at which the amplitude seems to be always the minimum, and antinodes, points in which the amplitude seems to be always the highest. For reference, we will take these points at 0 and L, the length of our string. As we can see in these equations, the amplitude of the wave will always be 0 at these 2 points, and since this property will not change over time, their derivative with respect to time will also be 0. But how can this be possible? You don't trust me? Let's look at the maths. So if we start with an expression for an addition of waves, in which A and B will be the amplitudes of our waves, omega their angular frequency, and k their wave number, in which the minus sign in the argument of the second wave represents the change of direction, we can clearly see that if we impose the condition at x equals 0 to find a knot, we can see that the x components of our expression will vanish, leading us to A and B being equal in magnitude but opposite in sign. If we apply this to the previous expression, we can easily see a trigonometric identity that lead us to the following expression. But we are not done yet. We need to impose also a knot in x equals L. For this to be true, the sign of KL needs to be 0. And if that's so, k times L needs to be a number of times pi, reaching the following expression for the wave number, n times pi divided by the length of our string L. Finally, applying both conditions to our first expression, we will find the following one, just by applying our physical boundaries, in which we can clearly see the true nature of nodes and antinodes. Antinodes, points where the two waves always interfere constructively, resulting in amplitudes twice as big as the original, and nodes, points of constant destructive interference, resulting in 0 amplitude.
This leads to a fascinating conclusion. If we equate our expression for the wave number to its classical definition, 2 pi over lambda, we see that only a discrete number of wavelengths can fit on the string, giving us the following waves, called harmonics. This is also applicable to longitudinal waves and with other boundary conditions. Longitudinal waves take the form of periodic compressions along a medium, moving parallel to the direction of travel. In an open-ended tube, the air is free to oscillate at both ends at maximum amplitude in a standing wave. Therefore, the ends of the tube must have antinodes. By imposing this condition, we reach the same result as for a closed-ended string. For a tube with one end closed and one open, the air at the closed end will instead be a node when there is a standing wave, only being able to fit a quarter of a wavelength, giving the following expression as a result. All of these wavelengths have associated a frequency due to the fact that we can express wavelength as the speed of propagation over frequency. These are the resonant frequencies, frequencies at which the transmission of energy of the driving force to our string is optimal, resulting in motions with great amplitudes. The lowest of these frequencies, i.e. n equals 1, is known as the fundamental frequency.
Moving on to applications. Some of the most common ones are the musical instruments with strings, such as guitars or violins, which use their resonance boxes to transmit the vibration of the strings to the air. Standing waves exist in nature too. They can be formed in the atmosphere in mountain regions, often exploited by glider pilots, or even on some fast-flowing rivers, being very popular with river surfers. One interesting device that works using standing waves is the microwave. It uses a 3D pattern of standing electromagnetic waves, in which the nodes correspond to cold spots, while the antinodes to the hot ones. Besides all of these examples, one of the most important applications is the use of standing waves to explain electrons' behavior. The electrons do not orbit the nucleus in the manner of a planet orbiting the Sun, but instead exist as standing waves. Thus, the lowest possible energy an electron can take is similar to the fundamental frequency of a wave on a string. Higher energy states are similar to harmonics of the fundamental frequency. These are the spherical harmonics that shape the atomic orbitals. Schrödinger developed an equation based on this theory, which represents the core on which quantum mechanics was built.